right, welcome ladies and gentlemen to lesson 2 for logarithms and exponentials. We're going to be looking at a couple of straightforward things today. We're going to be looking at the number e and the compound interest formulas. Now, let's just go ahead and start with the number e. The number e is sort of like the number pi, where we have represented a number as a letter. This is Euler's number. It is approximately 2.71828. And this actually ends up being a very important number in our study of exponential and logarithmic functions. Today we're going to be looking at it as a number and as part of the exponential side. And later, obviously, we will learn about the logarithmic side of it. So as a function, it looks like this. And since we can write it as a function, that means we can plug numbers in or substitute numbers in, and we can actually graph this. We're going to just do a quick sketch here, and we're just going to say, if my thing will work for me here, we can just say we have an x and a y table. And I'm going to do this one a little bit different than I have in the past. This is e to the x, the function itself. So if we think about just negative 1, negative 2, 0, 1, and 2, as we always do, we're going to say e to the negative 2, e to the negative 1, e to the 0, e to the 1, e to the 2. Now, on your calculator, this is something we can't really do by hand with the exception of e to the 0, we know is 1 because anything to the 0 power is 1. We know e to the first is just e, and we know e is 2.718. And the other ones we have to actually use our calculators for. There is an e button on your calculator. It might look like e with a little caret. It might look like e to the x. Either way, you should be able to find this on your calculator. It's usually on the left-hand side of all calculators. So if we went e to the power of negative 2, we get 0.135. If we say e to the negative 1, we get 0.368. And then e squared is going to be 7.389. Now, graphically, this should look exactly like our other exponential functions, where we know e is bigger than 1, and therefore it's going to be a growth. So it's a growing exponential function, or an exponential growth. And here we have, let's see, 1, 2, 3, 4, 5, 6, 7. Let's go up a little bit more and go up to 8. All right, and then we can go ahead and plot some coordinates. So 0.135, that's pretty close to the axis. 0.368 is up just a little bit more than a quarter. E to the 0 was 1. E to the 1 is 2.78. And e squared is 7.4 approximately. And look at there, we have our exponential functions, or function. So this is an exponential growth, and we should know that because the letter e, or the number e, is bigger than 1. And really, the important part here is to be able to find this on your calculator and use the e button appropriately, and just have this new number in your tool belt for later on, for later use. And one of those later uses is actually the next thing that we're going to be looking at. So we have this thing called the continuously compounded interest formula. Now, this is normally how your bank account works, if you have a bank account. And what it does is, if you put money into your bank account, your bank is going to be paying you money based on a percentage rate. And the equation that we are going to use for that type of idea is this. It's a very simple formula. This is A equals P times E to the power of RT. So this is our standard like exponential function where p times the exponential piece means p is my initial value. And in our study of this particular material, we call this thing, oops, let's not do that. We call it not initial, we do call it initial, but sometimes we call a little bit different stuff here. And that. A, we'll get to P in a second. A is the amount in your account or amount that you've received or is amount that you are worth now after a certain amount of time. P is what we call the principal, but in the function notation, as we've learned earlier, it's also the initial amount. It's the amount you have invested or the amount you started with. But with the terminology, we use the word principal. E is that number that we looked at on the last slide. R is the annual interest rate. And T is the time in years. Now, this is a pretty straightforward, very easy equation. All we have to do is be able to pick out the parts and understand that this is the formula we should be using. The most important words to know to use this equation is if it is compounded continuously. So when you see compounded continuously, that's when you use this equation. Our next slide has the one where it's not continuous. So when we have compounded continuously, we're going to use this. That means we are going to use A equals P times E to the RT. And we invest $1,050 at a rate of 5.5% after 5 years. So this is the amount we invested, that's P. This is my rate, which we need to change to a decimal as 0.055. And 5 years is T. That means we're going to figure out how much you have in your account. So we're going to say A equals 1050 times E to the power of 0.055 times 5. I do want to mention, if you are typing this in your calculator, you will want to do something along this line. You can actually write 1050 times E. If yours comes up as a caret, you need to put this in parentheses as 0.055 times 5. So that way it knows that the whole exponent is that product. And when you do this, you are going to get $1,382 and approximately 36 cents. And that should make a little bit of sense. You started with 1,000, now you have 1,300. So your money has gone up over 5 years because it's increasing by 5.5%. Okay, so again, the big important piece is to look for the statement compounded continuously. All right, so what about if it says not continuously? It actually uses different words. It doesn't say non-continuously. But the compound interest formula is one you may have learned in Algebra 1, or maybe not. So the compound interest formula here is when a problem says things like compounded quarterly or monthly, daily, yearly, anything like that where it doesn't say continuously. Continuously means always. It's always compounding. It's always getting bigger. So I'm going to stress this again. Obviously, this is not for continuously compounded interest. This is the formula. It looks a little bit complex, but it actually ends up being a very simple formula again. in the fact that we have a equals p times some number to a power of nt. Now, you will notice that this 1 plus a number means that it will be bigger than 1, so again, it's a growth function. A, P, R, and T are all the same as before. Those are the same exact things as they were on the last statement. The difference here is n. N represents the number of times per year that the interest is compounded. So if it says compounded quarterly, that means n would be 4. So I might as well write that in there. We can say that here n equals 4. If it's compounded monthly, n would equal 12. If it's compounded daily, n equals 365. If it's yearly, n equals 1. Now, it's not very fun, but n does equal 1 in this case. So, given a very simple problem, if I said you invested $1,500 at an interest rate of 1.5%, compounded monthly, how much money would you have in your account after 5 years? So the same kind of idea as we had on the last problem, only in this case it says compounded monthly. So this is important. It doesn't say compounded continuously. So we have A equals the amount you invested, that's your P value, your principal. The 1 is just a 1, plus my rate, 0.015, over the number of times compounded in the year. So that's monthly, so that means n is 12, to the n, which is 12, times the number of years, which is 5. And you might plug this into your calculator in a couple different steps. You might figure out what this inside piece is first, and then take it to the power of 60, because 12 times 5 is 60, and then multiply by 15. Up to you. You can type this in all at once, but that depends on how well you are with your calculators. So I'm going to do it all at once. And I get 1616.75. So $1,616.75. It does not seem like a lot, but in actually now day of age, the 1.5% is pretty standard, but your bank account is using a continuously compounded model, and that's going to change your outcome a little bit, and you'll see that in your assignment as you continue forward, or your other examples that you'll see in the textbook. All right, I am going to leave you again with a comic, and I hope you learned a little bit of stuff, and I will see you guys later.